Hi everyone. In this video we want to work on figuring out what the basic log shapes look like. So just like we added the family of exponential functions to our list of graphs we should know, we would like to add the entire family of log functions to the list of functions whose graphs we should know and be able to transform. So what we're looking at here is f of x equals 3 to the x, and f of x equals 1/3, g of x, give them a different name, equals 1/3 to the x. So first I'd like to say what function f inverse is and g inverse, and then I want to use what we know about graphs of functions and their inverses to figure out what the graph of g looks like. So if my function f of x is 3 to the x, its inverse better be a log base 3 of x. This is the entire reason that we created these log functions. And if my function g of x is equal to 1/3 to the x, then its inverse better be a log base 1/3 of x. Again, the log function you can write with or without parentheses. If you start getting really messy stuff inside the log function, you'll need parentheses to show what's inside the log and what's not. If there are no parentheses, you'd assume only the thing immediately attached to the log is inside of it. Okay, so if we want to get a graph of the log base 3 and the log base 1/3, we can use the fact that it's inverse of an exponential function. So to get the graph of an inverse function, we remember that we would flip across y equals x. See if I can carefully draw that in. So for example, the horizontal asymptote at y equals 0, x's and y's switch, so it becomes a vertical asymptote at x equals 0. So the log graph has a vertical asymptote at x equals 0. 3 to the x should go through the point 0, 1. If we flip across y equals x, it switches our x and y. We get the point 1, 0. 3 to the x goes through 1, 3. If we flip across, it should go through 3, 1. We can do this as much as we want to. It should also go through 2, 9, 3 to the x, which means this one, the log, should go through 9, 2. It should go through -1, 1/3, which means the log should go through 1/3, -1. Basically what happens is this little tail that was approaching the x-axis will become a little tail that's approaching the y-axis. And here, where f was getting very, very steep, f inverse is getting very, very flat. So it is increasing, but it's doing it very, very slowly. So this is what the log base 3 of x looks like. We know with the exponential functions that a 4 to the x looks fairly similar to a 3 to the x, and a 10 to the x is also a similar shape. They get much steeper in quadrant 1 and flatter in quadrant 2 as the base gets bigger. So logs will have the same sort of thing happening. A log base 4 of x will be very similar, but instead of going through 3, 1, it'll go through 4, 1. A log base 10 would go through 10, 1. So you can see they flatten out even more in quadrant 1 as the base gets bigger. And over here, they would suck back in towards the y-axis quicker as the base gets bigger. So basically, this is the general idea of the shape for any base bigger than 1. So not exactly that, the points will change, but that's the general shape you should get. You get this increasing log function, the vertical asymptote at x equals 0. For bases between 0 and 1, we get this exponential decay shape, which will have a related but not the same log graph to go with it. So the 1/3 to the x, let's see, it goes through 0, 1 as well. Oh, here, start with this. Has a horizontal asymptote at y equals 0, which means the log will have a vertical asymptote at x equals 0, just like before. So actually, it turns out that no matter what your base is, log base b of x has a vertical asymptote at x equals 0, always. The exponentials always go through 0, 1. So once again, regardless of your base, your log function should always go through 1, 0. And then 1/3 to the x goes through 1/3 1. I'm sorry, I'm saying it backwards. 1 1/3, so the log should go through 1/3 1. Let's snag one more point here maybe. 1/3 to the x goes through -1 3. So the log should go through 3 -1. You can snag more if you want, but what we should be seeing here is that this little tail that comes down and gets really close to the positive x-axis will become this tail that heads up and gets really close to the positive y-axis. So this little bit right here flipped across. Over here where we head into quadrant 2 and get really, really steep, the log graph will head into quadrant 4 and get really, really flat. See if I can sort of get that to happen. There we go. Okay, so the logs, it can almost get a little distracting looking at it with the exponential, but what I would like you to see is that the log shapes, just like the exponential shapes, they're really the same shape. In this case, it's a flip over the x-axis. If you flip this one upside down, you will get exactly this graph. So basic log graphs, you should know that they always have a vertical asymptote at x equals 0. They always go through the point 1, 0, but this I don't even know if you need to memorize. If you're getting logs, you should just be able to spot that no matter what log you're working with, the log base b of 1 is always going to be 0. Another good one is the fact that the log base b of b is always 1, which means it'll also go through the point b1. What else do I want to say about these things? The domain is always x greater than 0. Doesn't matter whether you're getting the increasing or decreasing log. That's always true. The range is always all real numbers. So again, it's a matter of remembering if your base is bigger than 1, you're going to get this shape. If your base is between 0 and 1, you're going to get this shape. And keep that basic idea in mind. I find that people actually have a really hard time remembering what that basic log shape is. So make sure you've memorized that before we get to test time. You're not going to get a calculator to check that. And we'll want to know these so that we can then apply transformations to them. All right, thanks for watching.